So, good afternoon. Welcome back. I hope you guys have had a good day so far. I hope yesterday went well. I hope that you're planning on enjoying this nice 4-day weekend coming up. Yeah, all those things. So, today we're going to be doing our Desmos activity for 7.2 and 7.3. Hopefully it helps make a little bit more sense of what we've been doing in class. And if it doesn't, we'll figure something out. But I'm hoping it works. So, to get started, I'm going to give you guys the link to the activity so you can join. All right, so the link to the Desmos activity should be in the chat. You should be able to click on that link and join the activity. The other option is to go to student.desmos.com, go to our class, and join the activity for 7.2 and 7.3. I'm also limiting you guys to the first screen. That is our check-in screen today. If there's anything you'd like me to know, please put it in there. If you'd just like an opportunity to vent, you can do that as well. That is up to you what you'd like to let me know of. So there's that. So let's take a few minutes. Let's get logged in. If you're having any issues getting logged in, or you can't log into the Desmos activity for any reason, please let me know so that I can help or figure some way to help you get logged in or work around, but I can't help if I don't know. Right. So I'll give you all a couple minutes to get logged in and answer that first check-in question. So we're gonna get started here. I'm not going to go through and read all of your guys' responses for the checking in right now. I'll do it after class because I read slow and I don't want to take up our precious class time reading those. But I will read them because I like to know what you guys write and how you're doing. So also keep in mind, right, that these Desmos activities count towards your grade, the participation in the class. These essentially are replacing the discussion boards and CYU assignments that we did last semester, right? These assignments, like I don't grade these on you guys doing them correctly or getting all the questions done or getting them on, like getting the right answers. You get credit for showing up and participating in the activity. I can tell if all you did was log in and you never typed anything into any of the screens or selected answers. If that happens, right, I look back in Desmos and see that you didn't actually participate, you don't get credit, right? Because it's just, you didn't do anything. Whoa, oops. Close that. Sorry. I don't know if you guys can hear that. That was my other video finished publishing, so it started playing. So sorry about that. Anyway, only simply logging in doesn't count, right? As long you need to log in and participate. You don't have to do it all correctly. You don't have to finish all the questions, but you do need to participate. So please keep that in mind. Otherwise, it just doesn't work out. Right. So with that, if you haven't logged in, please log in. Get your credit. Learn some stuff. It's gonna be great. It's gonna be fun. It's gonna be awesome. It's AP stats. Woo. All right. So we're going to get started. So we're going to open up the first screen. All right, so you guys should be able to move on to the second frame there. I'm leaving opening everything as we go. So please move on to screen number 2, which is kind of a review screen. I'm going to share my screen, so if you're following along at home and you're not in Desmos, or if you want to see what's going on my screen, right? It is shared now. All right, this is essentially one of the last slides from our presentation yesterday on section 7.2 and 7.3. It is the side-by-side comparison between sample proportions and sample means, right, of a sampling distributions. right? We can see the formulas and kind of rules that go along with sample proportions and the rules and the formulas that go along with sample means. Right? You will need these today. These will come in handy. Right? So you'll want to maybe go back to this screen and refer back to these rules from time to time. All right. So remember, the mean of a sample proportion, or the mean of the sample proportions, is equal to the proportion of interest from our population. Right? The standard deviation of our sample proportions is equal to the square root of the proportion from our population times 1 minus that proportion from our population divided by the sample size, which is n, as long as the 10% condition is satisfied. Right? We have to check the 10% condition in order to have a valid standard deviation. And as n increases, the sampling distribution becomes approximately normal. All right, we check the large counts condition in order to do normal calculations. All right, and the large counts condition is having at least 10 successes and at least 10 failures. Right. So n times p needs to be greater than or equal to 10, and n times 1 minus p needs to be greater than or equal to 10. That's our large counts condition. Sample means, right? The mean of sample means is the mean from the population. The standard deviation of sample means is equal to the standard deviation of the population divided by the square root of the sample size, n. And once again, the 10% condition must be satisfied in order to have a valid standard deviation. Right? If the population distribution is normal, then so is the sampling distribution of the sample means, x bar. The central limit theorem says that when n is large, greater than or equal to 30, that's our cutoff point, the sampling distribution of the sample mean, x bar, is approximately normal. Right? So we have our conditions and our formulas and rules and such for sample proportions and sample means. We need these. Please feel free to refer back to these or look at your notes. Okay. So now, we had a lot of problems to get through. I've tried to do this 2 different ways already today. We're going to try a 3rd different way today for you guys to try to make best use of our time and of your time. So what we're going to do, hopefully this will work, is we're going to do some breakout rooms. All right. So give me a moment. I'm going to set up some breakout rooms. We're going to use these rooms to work through the rest of the activity, essentially, or as much of the activity as you can get through. We're going to do 30 minutes of working time in your groups. Then we'll come back, we'll review, and we'll be done for the day. All right. So let's talk about these things. I saw a lot of good work going on, a lot of good responses for all of these questions are the ones that have been answered so far. I know that that was not enough time to thoroughly work through all of the problems, right? And that's okay. So we're going to go through these. We're going to talk about it. So I'm going to share my screen. You're welcome to follow along on your own version of the activity, or you can switch to see my screen as it is now shared. That's up to you, however you'd like to follow along. All right, so if we go to our first problem here, the SAT math scores problem. Let me zoom in a little bit. There. So in this problem, this is the proper sorting. We have a mu for the population of 515, a standard deviation, or sigma, for the population of 114. That's in the first sentence of the context. Right. We have an n, or SRS, sample size is 100. Right, so then the mean of the sample means is 515, based on the rule here for our sample means. And the standard deviation of the sample means is 114, standard deviation of the population, divided by square root of 100, which is the square root of our sample size. Right? And again, this comes from this rule right here in our standard deviation for sample means. Okay. So that is the first one. The next one, this is the correct pairing, so to say. In this one, there were 4 extra cards. They did not match to anything. Right? They are simply there to kind of throw you off, so to say. They're common errors in pairings of the variable and values. All right. In this case, oops, I zoomed in too much. We have a population proportion of 0.30, and it's the proportion that we're interested in, which is the proportion of college athletes that believe PEDs are a problem in college. The mean of the sample proportions is the same as the population proportion at 0.30, and that's from this right here of the sample proportions. Mean is mean of p hat equals p. And then the standard deviation of the sample proportions is equal to the square root of the population proportion times 1 minus the population proportion divided by the sample size. Sample size is 750. So those are the 3 cards that go along with this context. These are all just incorrect pairings that were left as extra cards, right? The proportion is not 750. 750 is our sample size. That would be n. P hat is not necessarily 0.3. We were not told what one of our p hats was. P hat represents the proportion of athletes who believe PEDs are a problem in a single sample. We could say p hat equals something, but we don't have that data. So that's why this one's wrong as well, right? So these are just kind of variations of common mistakes. Is there anything I can clarify about the first 2 card sorting parts of the activities? Right. 10% condition. Many of you had this correct. Of those of you who answered this question, you had, or at least you were on the right track. Right. The 10% condition is that the sample size should be at most 10% of the parent population. Okay, it has to be less than or equal to 10% of the parent population. If this condition is met, then the standard deviation of the sampling distribution of the sample proportions or sample means can be found. It means that we can find a valid standard deviation. Otherwise, we could calculate it, but it's just not usable. Okay, so that is our 10% condition. Is there anything I can clarify about the 10% condition? The large counts condition. The large counts condition applies to sample proportions. Right? This condition says that there must be at least 10 successes. Right? Success is n times p, so n times p must be greater than or equal to 10. And at least 10 failures in our sample. This is represented by n times 1 minus p. Both of those numbers need to be at least 10. If this condition is met, then the sampling distribution of the sample proportions is approximately normal, and we can use all the things that apply to normal distributions. So that is our large counts condition. The Scrabble problem here is applying these definitions. Right, so in our game of Scrabble here, each player begins by drawing 7 tiles from a bag containing 100 tiles. 100 is our population. That's the size of the entire population. There are 42 vowels, so 0.42 of the population are vowels, 56 consonants, 0.56, and 2 blank tiles, 0.02. Mr. Mosley chooses an SRS of 7 tiles, so n equals 7. P hat is the proportion of vowels in my sample. Is the 10% condition met? The answer is yes. This is because 7 is less than 10% of 100. Right, 10% of 100 would be 10, 7 is less than 10. We're good to go. 10% condition is met. The large counts condition is not satisfied. It is not met in this case. This is mainly because the sample size is 7, so it's impossible to have more than, or at least 10 successes. I can't get at least 10 vowels in a sample of 7. Can't have at least 10 failures in a sample of 7 either. So the large counts condition fails, so we cannot use a normal distribution or approximately normal distribution in this case. It doesn't fit. So we can't really calculate probabilities in this case with what we know. Is there anything I can clarify on this example? I didn't get to type this one in yet. So the central limit theorem, for our purposes in this course, what sample size n is considered to be large enough for the central limit theorem to be used? For this course, we're considering greater than or equal to 30, right? So the sample size must be greater than or equal to 30. CLT to be applied. All right. And what does it mean about the sampling distribution of X bar if the sample size n is large enough? If the sample size is large enough, then the sampling distribution of the sample means is approximately normal. And you should capitalize normal because it's like a pronoun as far as stats is concerned. So that's the central limit theorem is essentially the large counts rule for means. Right. All right. Is there anything I can clarify up to this point? Okay. So then I realized that most likely you guys did not get to question the slides 9 and 10 with the questions on them. However, I can show you how these were done. All right, so I'm gonna switch on over to that. Wrong example. That's the one I want. And I wanna zoom view. There we go. And one more. A little less. All right, so this is the same problem as is on slide 9. All right, we have a sample survey interviews and SRS of 267 college women. We're going to suppose that 70% of college women have been on a diet within the past 12 months. What's the probability that 75% or more of the women in the sample have been on a diet? Right, in order to do this, you will need to calculate the mean and standard deviation of the sampling distribution of p hat. Check the 10% and large counts conditions. Then, if the conditions are met, you can use normal calculations to find the probability. Excellent. So here we have it. N. Size of our sample is 267. P, the population proportion, is 0.70, right, 70%. P hat is equal to the proportion of women who have been on a diet from the sample survey. Right. Based on what we know, the mean of the sample proportions is 0.70, the same as the population proportion. 267 is less than 10% of all college women, so the 10% condition is met. Notice I'm not doing any calculation for this in this case, all right? And it's because it's kind of like, I can say this and it's generally accepted to be true, right? There's going to be more than 2,670 women in college, right? So we simply just have to state that this is a fact. Cool, we're good to go. We now find the standard deviation of the sample proportions, and that's equal to the square root of 0.7 times 0.3 divided by 267, and we get a standard deviation of 0.028. All right, since NP equals 267 times 0.70 equals 186.9, and n times 1 minus p equals 267 times 0.3 equals 80.1 are both at least 10, the large counts condition is met, and the sampling distribution of p hat is approximately normal. Right? Even though it seems like this is obviously true, it should be stated before you continue. We need to justify the fact that I can use normal calculations. Right? So that brings us to, we want to determine the probability that p hat is greater than or equal to 0.75. That's the original question. Right? What is the probability that 75% or more of the women in the sample have been on a diet? Right? That's here. This is equal to, using the complement rule, 1 minus the probability that p hat is less than or equal to 0.75. I use the complement rule because table A always gives me proportions to the left of a z-value. So I've used the complement rule. We standardize 0.75 using my mean and standard deviation from my sample. We get 0.75 minus 0.70 divided by 0.028. We get 1.79 approximately. That's been rounded to 2 decimal places because I only get to use 2 decimal places on table A. We go to table A, we find 1.7, 0.09, follow it down, we get 0.9633, which is then what I put in here, right? Because P of Z being less than or equal to 1.79 is equal to 0.9633. 1 minus 0.9633 equals 0.0367. This is the probability of there being more than 75% of women surveyed being on a diet within the last 12 months. And that's what we state at the end. There's a 0.0367 probability that 75% or more of the women in the sample have been on a diet within the last 12 months. Is there anything I can explain in more detail for you? Or anything you'd like clarified? So this is how we can work through that first problem. There's some steps to it. Right. If we look at the next one, the bad carpet example, there's going to be a lot of the similar steps, except now we're dealing with a sample mean instead of a sample proportion. Right, but we're answering similar types of questions. Right, with just the way that we calculate the mean and standard deviation, and we justify using a normal distribution changes. All right. So again, there. So we get a lot of the same beginning information. All right. Okay. That's okay, Liliana. Thank you for joining us. I know that the class is going to just slightly longer today. I apologize. We're almost done. Have a good day, Liliana. So we have the number of flaws per square yard in a type of carpet material varies with mean of 1.6 flaws per square yard and standard deviation 1.2 flaws per square yard. Population distribution cannot be normal because a count takes only whole number values. Normal distributions are continuous, whole number values are discrete, right? So we have an issue there. An inspector studies a random sample of 200 square yards of the material, records the number of flaws found in each square yard, and calculates X bar, the mean number of flaws per square yard inspected. We want to find the probability that the mean number of flaws exceeds 1.8 per square yard. Right? So we have a mean of 1.6, a standard deviation of 1.2 for the population. N equals 200 square yards, and X bar is the number of flaws per square yard in the sample. The mean of X bar is 1.6, the same as the mean of population. Since 200 square yards is less than 10% of all the carpet, 10% condition is met. We're assuming this to be true because they didn't tell us otherwise. Right. Standard deviation of X bar is then 1.2 divided by the square root of 200. That is our formula, and we get 0.0849 approximately. Since n equals 200 square yards is greater than or equal to 30, the central limit theorem is satisfied the sampling distribution of the sample mean X bar is approximately normal, right? Just because the parent population is not normal, the sampling distribution can be, right, because we actually end up getting a more continuous distribution. It's closer. It can be approximated by a normal distribution. So we go through basically a similar type of calculation as we did in the previous problem. We have the probability of X bar being greater than 1.8. I use the complement rule again to switch this into a less than or equal to type problem. Right. We standardize 1.8 minus 1.6 divided by 0.085. We get 2.35. That is what we then find on table A. We get 2.3. 0.05. We get 0.9906. That goes in for 1 minus 0.9906. We get 0.0094, a little less than 1%. So there's a probability of 0.0094 of finding that the mean number of flaws is greater than 1.8 in a random sample of 200 square yards of carpet. Pretty low chances. All right. I know that was a lot. I know that was fast. These solutions will be posted into Canvas so you can peruse them at your own speed and leisure. Other than that, the last screen here, if you don't mind, please do a quick little piece of feedback on how the lesson went. If you didn't like it at all, please tell me so. That works too. I'm open to all and any feedback. That all helps me, and it ultimately helps you guys. So please do that if you like. And as you're doing that, stop sharing my screen. If you've been doing the practice problems from Canvas for section 7.1 through 7.3, the solutions are now posted. I apologize, that took me longer than I wanted to get those ready, but they're ready and they're available, so you can check your work if you want. I do not quite have the assessments ready, so I do apologize about that. I'm hoping to have them ready by Friday. I know Friday's a holiday, so they won't be like due for a little bit after that, so don't stress on those yet, but they will be available soon. Other than that, if there's any other questions, anything else you need help with, if you feel you need other help, other examples, other things posted, please let me know. I'm more than happy to help. If you have questions and you want them answered now, please stick around and ask. Otherwise, remember, it's a long 4-day weekend. You do not have school on Friday or next Monday, so you just have one more day of school to get through this week. And you only have to see your 246 classes once this week. So there you go. Other than that, have an awesome rest of your day. Have a great long weekend, and I will see you next week.